Why does ice float on water? What do hair straighteners actually do to the hair molecules? And why are intermolecular forces essential to life? These are just some of the questions that we're going to take a look at in this video, where we're going to explore what intermolecular forces actually are. There are three different types of intermolecular force, but generally what they are is an attractive force that exists between molecules. And that's what the inter part of intermolecular force means. It means between molecule forces. These three different types of intermolecular force are called van der Waals forces, permanent dipole-dipole forces, and hydrogen bonding. And you need to know how each of these comes to pass. And you also need to know that van der Waals forces are the weakest, then permanent dipole-dipole, and then hydrogen bonding. But what they all have in common is that one region of a molecule is attracted to another region of a neighbouring molecule. And this is usually because one of these molecules is slightly positively charged and another region is slightly negatively charged. And I go into more detail about polarity in a different video. The strength of these forces influence a number of things, but the key properties are melting point and boiling point. And molecules that have got stronger types or more intermolecular forces will have a higher melting point and boiling point than molecules with weaker forces or fewer forces. The simplest intermolecular force is called permanent dipole-dipole forces. This is actually the second strongest intermolecular force, and it occurs between polar molecules. This is molecules that have got a permanent dipole. Dipoles occur where you get a covalent bond between elements that have got different electronegativities. What that means is one of the atom has a greater power to attract the electron density in the covalent bond than the other, and so the electrons are pulled towards one of these atoms, making it partially negatively charged and leaving the other one partially positively charged. And so the permanent dipole in one molecule can be attracted to the permanent dipole in a neighbouring molecule, in the way that I'm showing here. Now, the chlorine is attracted to the hydrogen in this particular angle that I've drawn, but all sorts of other angles and orientations are possible, could be end to end, side to side. But this force is always going to be there, because there is always going to be this electronegativity difference. It's permanent, hence the name permanent dipole-dipole forces. It's important to note that whilst some molecules have dipoles in a particular bond or a number of bonds, they can actually end up being non-polar if they are symmetrical molecules. What that means is the dipoles are ending up cancelling each other out, and we say that this molecule has no dipole moment, and that means that the molecule as a whole will be non-polar, and so there won't be any permanent dipole-dipole forces between molecules of this type, and therefore the boiling point might be a little bit lower than you might expect. You can actually do an experiment to prove that a molecule is polar rather than just whether it contains polar bonds. And in this experiment, what you will do is you'll set up maybe a burette containing your substance that you're wanting to investigate, and you start to let that liquid out through the tap with a steady stream flowing, and then you take a charged rod that's been charged using friction to transfer electrons between the rod and the cloth, and the liquid will bend towards the charged rod if it is polar, and it will do nothing if it is a non-polar liquid. The bending is always towards the charged rod, and that's because a polar molecule, and therefore a polar liquid, will be able to orientate itself favourably to attract towards the rod, whether the rod is positively charged or negatively charged. So for instance, if it was water and you held up a charged rod near to the stream of running water, the hydrogen would be attracted to the charged rod, the electron deficient hydrogen. Whereas if you charged a rod with a positive charge, then the oxygen part of the water would be attracted towards the positive rod. And this proves that a molecule, for instance water, does have a dipole moment, meaning that the molecule contains a permanent dipole, not just a polar bond. Hydrogen bonding is the strongest type of intermolecular force, and it has a lot in common with permanent dipole-dipole forces, but it is just a particularly extreme example of how two molecules can be attracted to each other. It's crucial to life as we know it. Without hydrogen bonding, so much wouldn't happen that we wouldn't actually be alive in the way that we are today without them. And we'll explore that more in a moment. But actually, what is a hydrogen bond? Well, a hydrogen bond is an attraction between a molecule that has got a highly electronegative atom, such as oxygen or fluorine or nitrogen. Those are the top three. And it's an attraction between the lone pair on one of those three types of atoms and an electron-deficient hydrogen in a neighbouring molecule. And so in order for a hydrogen bond to occur, we need to have those two features within the molecules that are forming that hydrogen bond. And so as a result of that, I have a slightly silly way of remembering it. We need the hydrogen, which is electron deficient, and we need the highly electronegative fluorine or oxygen or nitrogen with its lone pair of electrons. You could be asked to draw the hydrogen bond between two molecules. They might be the same molecule or they might be two different types of molecule. You could be asked how this hydrogen can come about. And when you do that, it's really important to label all the partial charges and the lone pairs, not just the one that is involved in the hydrogen bond between the lone pair on the electronegative atom and the electron-deficient hydrogen itself. When you draw them, it's also important to get the bond angles correct around that hydrogen that's forming the hydrogen bond. This hydrogen only has two pairs of electrons around it. That's the one in the covalent bond between it and, in this case, the oxygen, and the hydrogen bond, which is the lone pair of electrons. And so as a result of that, it will be linear around that hydrogen atom, and the bond angle will be 180 degrees. Van der Waals forces might be the weakest type of intermolecular force, but they're present in every single simple molecule, and their presence is really, really important because without them, particles would be existing as vapours rather than liquids or occasionally solids, and so life as we know it would be completely different without van der Waals forces, and you could go so far as to say that it wouldn't be possible as we know it. Van der Waals forces are sometimes known as temporary dipole, induced dipole, and that's actually a really helpful name because it helps us to understand how the force actually comes to pass. First of all, it's important to note that electrons are not static and they are moving all the time within their orbitals. So this means that at any particular moment, there could be more electrons in one part of a molecule than another, as I'm showing here. So you can see from this picture that I've drawn a certain number of electrons and I've drawn more of them over on the left-hand side than I have on the right-hand side. And this is because of random movements of the electrons in the molecule. As a consequence of this movement and this organisation of the electrons, the left-hand side of the molecule is a region where there are more electrons and it is electron-rich. The right-hand side of the molecule is going to have fewer electrons compared to that, and therefore it will be electron-deficient and therefore delta positive. This then sets up a dipole in this molecule. It's only temporary because these electrons are going to then move not long after they've been in this particular position. Before the electrons move again, though, the molecule that has this temporary dipole is likely to come into contact with a neighbouring molecule. And when it does so, the electron-rich region in the temporary dipole molecule causes the electrons to move in a neighbouring molecule. And that's because we get repulsion between the electrons. And so what that means is the neighbouring molecule has its electrons moving to the left-hand side, as I'm drawing it here, and therefore this causes a new dipole to come to pass in this neighbouring molecule. And to induce is another way of saying to cause. And so what we've got is we've got a temporary dipole that is causing there to be an induced dipole in a neighbouring molecule. And now what happens is the delta minus region in the temporary dipole, as I've drawn it, will be attracted to the delta positive region in the induced dipole. And this is what the van der Waals force is. But the reason that this type of intermolecular force is so weak is that the electrons will be on the move again and they'll be in a different arrangement, and this temporary dipole is likely to disappear or change completely because the electrons will move to a different position within the molecule. And that's what makes these the weakest type of intermolecular force. The strength of van der Waals forces depends on two main things. Firstly, the number of electrons that there are within a molecule, and that's because this affects the magnitude of the temporary dipole. If we've got loads of electrons, if there is an imbalance in where these electrons are positioned, we could get a huge dipole set up, which will mean it's going to be hugely attractive to its neighbouring molecules and therefore being a stronger force. Additionally, the size of the atom or the molecule can have a huge difference because this can affect the surface area of contact between the two different substances. So, for instance, the group 0 elements, as we work our way down the group, the atoms get larger and they have more electrons, and so as a result, the van der Waals forces between these group 0 elements will increase and the boiling point will increase as we go down the group. Similarly, the group 7 elements, they exist as diatomic molecules, but the atoms within these molecules get larger as we work our way down the group, and they have more electrons, and so there will be stronger van der Waals forces, and these substances will have higher melting and boiling points as well. And as a consequence of that, we have the interesting feature that in group 7, fluorine and chlorine are gases because their van der Waals forces are suitably weak that room temperature has enough energy to make these particles vaporize, whereas bromine is a liquid at room temperature, which means that the van der Waals forces are strong enough to keep this molecule in liquid form rather than turning into a vapor. In iodine, this is actually a solid at room temperature, and that means that the van der Waals forces are so strong that room temperature does not have enough energy to make these molecules separate, and this exists as solid crystals. Some simple molecules are so large that their melting point can be particularly high, and so room temperature doesn't have a chance of melting them. Things like this will be polymers, for instance, and they are very, very long molecules, so that means that there will be lots of electrons within them, there'll be many dipoles within the molecule, and therefore there will be strong forces between one polymer and all of its neighbours, and so the melting point of polymers is typically quite high, and that's why we can use solid plastics for so many different useful things in the wider world. Van der Waals forces can also vary based on the surface area of things like alkanes and hydrocarbons that might typically be linear, but they can have isomers which are branched. For instance, if we consider something such as butane, if we get two molecules of butane, they can line up nicely next to each other, and there will be a big surface area of contact between them. If we have methyl propane, which has got the same molecular formula, this structural isomer can't quite tessellate so nicely, the molecules don't fit together so well, and there is not such a good surface area of contact between these molecules, and so as a result of that, the melting point will be weaker because the van der Waals forces will be weaker. And this pattern would carry on for larger molecules with more branching, and that difference in melting and boiling point would be more significant. One of the questions that you can be asked about intermolecular forces is about the property of boiling point. And you might be asked which of the following could have the highest boiling point. And when you're doing that, what you're looking for is the molecule that's got the strongest intermolecular forces. And so we're most likely to be working our way through the intermolecular forces, seeking the one that's got hydrogen bonding. And so what we're going to look at here is butane. Butane only has carbon and hydrogen atoms in it. There is such a small dipole within the carbon to hydrogen, it's not worth considering. And the molecule is symmetrical, so definitely no dipole moment in hydrocarbons. So that means that there will only be van der Waals forces in butane, and so the boiling point of butane is likely to be very low. Butanal is an aldehyde. It's got the highly electronegative oxygen atom, which means there'll be a dipole between the oxygen and the carbon, but none of the hydrogen is electron deficient, which means there won't be any hydrogen bonding. And so that means that two molecules of butanal will be attracted together by permanent dipole-dipole forces. Butan-2-ol has got the oxygen, of course, of the alcohol group, but it's also got the electron-deficient hydrogen atom that's connected to the oxygen. And so that means that butan-2-ol will have hydrogen bonding between its molecule, which is the strongest type of intermolecular force, and so that means that it is likely to have the highest boiling point as a result of that. In an exam question, you might be asked to interpret a pattern in boiling points as you move down a group. So, for instance, as we've already mentioned, the noble gases, as we move through the different periods, the intermolecular forces, those van der Waals forces, get stronger, and so the boiling point increases. And then the same thing can be applied to the hydrides. That's particular elements bonded to hydrogen. And so if we take the elements of group 4, the pattern is again what you would expect. The boiling point increases as we move down through the periods. So methane has the lowest boiling point, then silicon tetrahydride, then germanium, and then tin. And that's because tin has got more electrons and stronger van der Waals forces. The patterns hold true when you look at the elements in group 5 as well. At least it does for the 3 of the elements, antimony, arsenic and phosphorus. But then when you get to nitrogen, the nitrogen hydride has a higher boiling point than you would expect. You would expect the boiling point to be somewhere around here if that pattern continued as we work our way up through the different areas of the group. But the boiling point is elevated for ammonia, NH3. And we get the same thing if we look at group 7 and group 6. The boiling point follows the pattern that you would expect. It decreases as we work our way up the group, except for water it is really, really high, far higher than we'd expect. And for hydrogen fluoride it is as well. And so you need to be able to interpret the van der Waals force influence region. In other words, a bigger molecule will lead to stronger van der Waals forces and a higher boiling point. But you need to be able to point out that there are exceptions for water, hydrogen fluoride and ammonia, and that's because these substances have hydrogen bonds between their molecules, which is the strongest type of intermolecular force, and so their boiling point is higher than it would be if we were just relying on van der Waals forces alone. You might have noticed that the elevation for water's boiling point was greater than it was for ammonia and hydrogen fluoride. And that's because water can, on average, have more hydrogen bonds per molecule than the other two. And that's down to the fact that water has 2 lone pairs on its oxygen atom and 2 electron-deficient hydrogen atoms, whereas the other two don't have that balance between those two qualities. Ammonia has 3 electron-deficient hydrogen, but only 1 lone pair, and hydrogen fluoride has 3 lone pairs, but only 1 electron-deficient hydrogen. And so that means that the balance is not the same, and so that they can only have, on average, 1 hydrogen bond per molecule, whereas water has 2. As I've already said, hydrogen bonding is absolutely essential for the existence of life itself. And that's for a number of reasons. Chiefly, though, proteins, which make up so many components in living things, have hydrogen bonding between different regions of the chain, and that gives it its 3-dimensional structure, and that keeps the pleated sheets or the alpha helices in the particular arrangement and shape that they have in 3-dimensional space. And so without that, proteins wouldn't have their 3-dimensional structure. Additionally, DNA, arguably the most important molecule in all of living things, that has an alpha helix structure, which is a double helix, and those 2 strands of the double helix are connected by hydrogen bonds between the base pairs. 2 hydrogen bonds for one of the type of pairs and 3 for the other. And without those hydrogen bonds, DNA would literally fall apart and would be 2 separate strands, and so life as we know it wouldn't be able to happen. Another feature of the world that is down to hydrogen bonding is ice and its low density. And this comes back to the fact that water can form 2 hydrogen bonds per molecule. When it forms its crystal structure that we find in ice, these 2 hydrogen bonds per molecule are in a fixed sort of tetrahedral arrangement. And what this means is the separation of the water molecules in this crystal structure is larger than it is in water. In water, the molecules are constantly on the move, and so their hydrogen bonds will only be short-lived and they're not in a fixed position. Whereas in solid water, they're in a fixed position, they organise themselves in the most stable arrangement as they form into that solid, and this is one with lots of spaces between the molecules and so a low density. Relating to water's ability to form hydrogen bonds is the property of solubility. Simple molecules are sometimes soluble, sometimes insoluble, and this is chiefly down to whether or not they have the capacity to form a hydrogen bond with water. If they can form hydrogen bonds to water, they're likely to be soluble. If they can't form hydrogen bonds to water, they're likely to be insoluble. And that's because water is a polar molecule, and so polar substances will dissolve in polar solvents. And non-polar substances can't dissolve in polar solvents. They need non-polar solvents in order to be soluble. And last of all, not quite such profound impacts of hydrogen bonding, but perhaps more immediately obvious in day-to-day life, hair straighteners and also ironing. Both of these work on the same principle. Hair can get curly due to hydrogen bonds forming between different parts of a piece of hair. And when you use your hair straighteners, what happens is the heat and the pressure breaks these hydrogen bonds and the molecules realign into a straighter arrangement. And the same is true of ironing. When you iron clothes, the iron provides the high temperatures needed to break these hydrogen bonds in the crumpled material, and the pressure as you push downwards with the iron, that helps the molecules to realign into a new position which is much flatter. And then you take the iron away and new hydrogen bonds form, and that keeps the molecules in their newer positions, and that means the fabric is flatter. Okay, that's the end of this video. I hope it was useful. I'll see you again soon.